workbook. Question 1. A candy bag contains 15 green, 12 blue, and 10 red, and 8 orange candies. You will choose 3 candies from the bag without looking. Which answer choice describes an event that is not certain in this context? All green candies. You're only picking 3, so you can't pick all 5. The bag full of candies, all combinations of 3 candies where at least 1 is green, and all combinations of 3 candies. So which answer choice describes an event that is not certain in this context? All green candies is not certain in this context. Nope. Okay, let's start again. Alright, lesson 24 workbook. So question 1, a candy bag contains 15 green, 12 blue, 10 red, and 8 orange candies. You will choose 3 candies from a bag without looking. Which answer choice describes an event that is not certain in this context? Okay, we have all combinations of 3 candies where at least 1 is green, all combinations of 3 candies, the bag full of candies, or all green candies. Okay, well, an event of this could be all 3 candies. So that is certain. We could have all combinations of 3 candies. We could also have the entire bag full of candies. So that's an event that is certain. I could take an entire bag full. Or another event is that I could have all of the green candies. But what's not certain is that I cannot guarantee that 1 is green. At least 1 is green in all of those combinations of 3 candies. So let's check that answer. Great job. Okay, so question 2. You write the letters of the word regulation on separate slips of paper and place them in a bowl. Your friend will draw a slip of paper out of the bowl without looking. What is the sample space of this experiment? Okay, well, sample space is written as a set, so I know that this one is not an option because it's not written in set notation. And then it says you write the letters on separate slips of paper. So one slip of paper is going to have an R, one slip of paper is going to have an E. So it's the set of each of those letters individually. So let's check that for grading. Great job. Okay. Question 3. Suppose you have a standard deck of 52 playing cards. Of the first of the 4 suits, hearts, diamonds, clubs, and spades, hearts and diamonds are red cards, and clubs and spades are black cards. What is the probability of drawing a red card if you draw 1 card from the deck? So, the probability of X such that X is a red card equals 26. Well, that's the number of red cards, but that's not our probability. Probability has to be less than 1. So that's off the table, and this is off the table because probability has to be less than 1. So what's the probability that x such that x is a red card? Is it equal to 1/4? Or probability of x such that x is a red card? Is it equal to 1/2? Well, we have that the number of cards we have is 52. That's our sample. That's the number of events in our sample space, and the number of drawing a red card would be half of 52, which is 26. So the probability of drawing a red card, would be equal to 26, the number of different ways we could draw a red card, and divided by our total options. So 26 divided by 52 does reduce down to 1/2. So there we have our 1/2. Let's check it before we move on. All right, great job. Okay, there are many players on the baseball team. Each player's number of hits compared to their number of bats is recorded as their batting average. Goran's batting average is .3, Riaz's batting average is .258, and Alistair's batting average is .333, and Horatio's batting averages is .289. Based on batting averages, blank one is most likely to get a hit the next time he is at bat, and blank 2 is least likely to get a hit next to bat. Okay, which one is the largest? And that would be Alistair's. It's .333. So Alistair is blank 1 because .333 is the largest out of .3, .258, .289. And then which one's the least likely? So which one's the smallest? And that would come down to .258. And that is Riaz's. Okay, and the way I look at these is since they're all decimals, I'm just kind of looking at it like, is 300 bigger than 258, or bigger than 333, or bigger than 289? I know that's not mathematically correct because they are not in the hundreds, and because they're representing decimals, but since they are all decimals, I can compare them that way. Since they're all decimals that are less than 1, let me just say that. Because if we had 1.289, then that would affect how I would look at it. But since they're all decimals that are less than 1, I'm just looking at the decimals as, okay, that's 300. And I'm looking at this as, okay, that's 289 in my mind, just to compare it, to make it a quick comparison. Submit that for grading. Great job. All right, you have chosen the, oh, I haven't answered question 5. So read each of the following situations in order to determine if it is a certain event or an impossible event, then follow the instructions. Okay, rolling a number less than 7 on a standard 6-sided die. Okay, well, since all of the numbers are less than 7, that is a certain event. Drawing a heart, diamond, club, or spade card from a standard deck of 52 playing cards. That's a certain event because you can do that. Okay, situation B is a certain event. C, rolling a 10 on a standard 6-sided die. That's not even an option on a 6-sided die. It goes 1 through 6. So situation C is impossible because I cannot roll a 10 on a 6-sided die. Drawing the 20 of hearts from a standard deck of 52 playing cards. Alright, well, there's not a 20 of hearts, so situation D is impossible as well. Let's come down here and submit that for grading. Great job. All right, question 6. The students in your math class are given a poll asking whether they like basketball, baseball, both, or neither. The following Venn diagram represents the results. Which areas of the Venn diagram shows the complement of someone liking basketball? You must select at least 2 answer choices. If only one answer choice is correct, select only and the correct answer choice. Okay, well, basketball is in blue. So, that's represented by area B. So anything that's not in area B is the complement of someone liking basketball. That's everything outside. So we have area A. Area C is included in our area of basketball. So area C is not a complement. We have area D, and so we have that areas A and area D. Whoops. And I'm questioning area D because part of area D. All right, there we go. I wasn't 100% sure with area D since in my mind it was partially included in area B, but since they labeled this intersection right here as area C, that is why area D, so everything outside of that was excluded when we excluded area C. So that's why area D still was the complement. If they hadn't identified area C right here, then I would not assume that you could count area D because some of area D lies in the basketball area of the Venn diagram. But since they did label it, then we could say area D was outside of that and it is the complement. All right, question 7. You roll a standard 6-sided die. What is the complement of the event x such that x is an odd prime number? Okay, remember that 1 is not a prime number. Okay, well, the event they're asking us for would be 3 and 5 because we only have 6-sided die. So what is everything else? Well, there's a 1, a 2. I can't list 3 because 3 is an odd prime number. 4, I can't list 5 because it's an odd prime number. 6. So then that would be our complement. This is our event that we were looking at, and this is the complement of it. So it would be 1, 2, 4, 6. Okay, question 8. You roll a standard 6-sided die. Which expression will calculate the probability of not rolling a prime number? So this is the complement rule. So we're going to find the probability that x is a prime, and I'm just going to shorthand it, is going to equal 1 minus the probability that x is not a prime. So that's what we're going to look for. So we're going to look for the probability of x such that x is not a prime number. I said this completely wrong. Okay, Question 8. You roll a standard 6-sided die. Which expression will calculate the probability of not rolling a prime number? So we want the probability that x such that it's not a prime. And I'm shorthanding it. That's going to equal 1 minus the probability. Well, what's the complement of not being a prime? It's being prime. So we're going to look for something that says probability of x is not a prime number is equal to, so this first one is off because we have minus 1 right from the get-go off of it. So we have probability that x such that x is not a prime number equals the probability that x is a prime number minus 1. No, that would end up with a negative because all probabilities are less than 1. And so if you subtract 1 from it, you'll end up with a negative number, and you cannot have a negative probability. So then probability of x such that x is not a prime number is equal to the negative x such that x is a prime number. No, we cannot have a negative probability. So probability that x such that x is not a prime number is equal to 1 minus the probability of x such that x is a prime number. That's our complement rule. So there's question 8. Great job. Moving right along. Question 9. Consider the standard deck of 52 playing cards. If H is equal to X such that X is a heart card, so if H is the set of heart cards, and K equals X such that X is a king card, so K is the set of king cards, what is the intersection H and intersects K equal to? Alright, well, let's think about this. H is a heart card. So if I were to list out all of the hearts, I could have a 2, 3, 4, 5, 6, 7, 8, 9, Jack, Queen, King. Alright, that's H, the set of H. Now the set for K is equal to the king cards. So the king of hearts, the king of clubs, and I can't draw king of clubs, king of spades, those are our upside down hearts, and the king of diamonds. That is our set. Okay, well, what is the intersection? What do these two sets share? They share the king of hearts. That's what they share. So that is what our intersection is they share the king of hearts. Great job. Okay, what is the probability of drawing an ace card from a standard deck of 52 playing cards? Okay, well, probability that we have an ace is going to equal how many ways can I draw that ace over my total number of outcomes. So I'm just going to say S. So this number of times event that an ace can happen is 4, because there's 4 aces, and the event from a 52 playing cards is 52. So we can type in 4 divided by 52. Great job. All right, question 11. Use the sets A is equal to the set 2, 3, 4, 7, 8, 9, and B is equal to the set 2, 4, 6, 8 to answer the following question. Which answer choice shows the union of sets A and B? Okay, so the union is A union B. So it's the U looking symbol. That's how I remember union. U, uh, the union sign looks like a U, and the intersection sign looks like part of an A, because I associate intersection with the word and union. I just explained that wrong. Okay. Let me get this straight in my mind. Okay, question 11. The sets A equals the set 2, 3, 4, 7, 8, 9, and B is equal to 2, 4, 6, 8. To answer the following question, which answer choice shows the union of sets A and B? Okay, well, is this a union or an intersection? And this is the union of them. This is all of it together. So A union B is going to equal all of the sets. So we have a 2 and a 2. I'm not going to write it twice because it's repetitive. We have a 3 from set A. We have a 4 from set B and set A, so that takes care of that. And I'm not writing it twice because it's repetitive. We have a 6 from set B. We have a 7 from set A. We have 8 from both sets. And we have a 9 from set A. So the union of the sets is all of them together. So we have 2, 3, 4, 6, 7, 8, and 9. Now we need to decide which symbol represents union. Is it the upside down? It looks like a U, or is it upside down looking like part of an A, an upside down U? And it is this one, the one that looks like a U. A union B. This is A intersects B. So the one that looks like a U represents union. Let's check that. Excellent job. So that's just how I keep track of union and intersection. The union symbol looks like a U. Okay, let's move on to question 12. You write the letters of the word demographics on separate slips of paper and place them in a bowl. Your friend will draw a slip of paper out of the bowl without looking. What is the probability that your friend will draw a vowel? Okay, well, what is our sample space? So the probability of a vowel is going to equal how many different vowels there are divided by how many total letters there are. So our vowels, there's 1, 2, 3, 4. There are 4 vowels. And then how many total letters? Well, we have 4 already because those are our vowels. 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 total letters. So we have 4 out of 12 chances, or the probability. Great job. All right, so there is your workbook for lesson 24.